right, folks. Hey, welcome day 3 here. Here we go. So with day 3, what we're going to see is we're going to talk Brian on the beam. All right. So now you got some different pictures of torque on the top, and then really our Brian on the beam on the bottom over there on the bottom right. Okay. So when we talk Brian on the beam, really what we're calling this is a generic name for, or a specific name for mechanical equilibrium. Right. So when we talk mechanical equilibrium, there's a couple things that we'll talk through first prior to actually running through the completion of the problem. Okay, first for us, for an object to be at mechanical equilibrium, it must have the sum of its forces, the sum of its forces is equal to the net force, which is equal to the imbalance, which is equal to 0. That doesn't mean we have no force here. What it does mean is it means that we have all of these forces are exactly balanced out. If you think about it, when we talk about equilibrium, our forces are going to cancel out. If you look back to chemistry land, right, when you talked about equilibrium there, the forward reaction was the same as the backward reaction. So you made as many reactants as you did products. Now, we've talked about equilibrium before, where we talked about an object, standing on a chair and the chair pushing back up against the person, right? So it's a similar concept for us. We're just using it now to talk through some concepts of torque. Okay? Do things in a mechanical equilibrium have to be stationary? This is a key question for us. Now, for our purposes, everything is going to be stationary. But in other cases, is this true? The answer is no. As long as your velocity or your angular velocity are constant, we should be all right. Here again, think about the car driving down the interstate. You got the cruise set. So your forward forces are going to be balanced out by your backward forces. The reason is there's no acceleration. There's no change in that unbalanced force. The force is getting canceled out by the backward force. Think of terminal velocity jumping out of a plane. All right. All of those become very crucial for us. You can also look at and say, hey, spinning. Well, if we're spinning at the same rate, left and right, or left and forward, or right and forward, whichever way you want to go, then yes, we are stationary there as well. Now, a couple key points. V is our velocity in meters per second. That omega, that fancy W, is angular speed. It's how fast something spins, radians per second. We've gone through now a couple days worth of trying to convert revolutions per minute into radians per second. So that becomes something big for us to remember. Here we go. So Brian has a weight of 800 newtons. How much force would the ground need to have to balance out Brian's weight? Now, I know what you're thinking. You're thinking, hey, this is exactly like third law again. We've already done everything like this. We know that he's pushing down with 800 newtons. We know there's a normal force pushing back up. Exactly, that's what we're looking at again. So we say if he's pushing down with 800 onto the ground, then the upward force for us should be exactly the same at 800. Not trying to trick you, not trying to fool you, just trying to make sure that we get this first beginning base layer of concept down. So what happens if the board weighs 500 newtons? What is the total downward force? Once again, if it's all acting in the same direction, we can add it together. So the total downward force would be 1,300 newton. Okay? If we put in Mighty Mouse, I don't know if you know Mighty Mouse, back in the day when I was a young little whippersnapper, Mighty Mouse was a big deal. You probably got no clue who he was. That's okay. So how much force does Mighty Mouse have to exert to hold up the board and Brian? Well, we know that if there's 1,300 newtons of force downwards, in order to make this completely balance itself out, the upward force has to be the same. It has to be 1,300 newtons. Now, granted, this is a very, very funny example because we're using a cartoon character, but really that becomes a big deal for us. If you think about, having a diving board or something like that, you have to be able to have some sort of upward force to balance that thing out. Otherwise, it's just going to flip and fall. So we have Brian again. 800 newtons is standing on a 10-meter long, 1,000 Newton beam that is supported by a cable at each end. So think of the window washer example that I used on the previous picture. You could look at it as scaffolding on the side of a house if somebody's putting up new siding, right? It could be a cherry picker lifting something up. I mean, there's all kinds of different applications for us here. So what we want to know is, what is the tension on the left cable? Now, tension for us is force. Don't start thinking about, hey, I got to do, MA minus MG. No, there's not. This is stationary. We don't have to worry about that component of it. So what we do is we start putting in our number. The tension on the right cable is 600 newtons, and that's pulling upwards. So that's pulling the side up. The left cable, that's the one that we don't know yet. All right. But what we do know is we do know that Brian has an 800 Newton force downward. We do know that the beam has a 1,000 Newton force downward. Now, again, those two things are pushing downwards, right? Yes, there is a normal force. In this case, the only way that we can balance this out is with the cable on the right, cable on the left. So what we have to do is figure out, all right, how much total downward force is there, so that we can balance that out by how much upward force we want to get to. Now, if we look at this, here's a question for you. Should the force on the left side be bigger or smaller than 600 newtons? The hope is that you're saying is it should be bigger than 600 newtons. Now, in the picture, we set you up so that he was standing on the left side. I get that, right? But if you think about it, right, and look at the total amount of force that we have down, it gives you at least a little bit of an understanding that he should be farther left. All right, so that force should be bigger. So if there's 1,800 newtons of downward force, and this is the other part of it that I'm looking at, right? If we see that that right side one has 600 newtons, and the total downward force is 1,800 newtons, then we know he's not standing in the middle. Otherwise, it'd be split even. For us, we know that there's more force on that left side. So because there's 1,800 downward, and we know the right cable goes upwards with 600, the left cable has to produce 1,200 newtons of force in order to make sure that this thing stays level and does not drop, move, flip, turn, or twist. All right? Hopefully finding force like that is pretty easy, pretty straightforward. So then we start to go on to, all right, now, how do we actually find how far from the left cable Brian is actually standing? Okay, so for us now, if we know all of our forces involved, remember, torque is just force times distance, right? So because it's force times distance, we have to choose a pivot point. That's the biggest thing. Remember, torque is this twist. We're always going to get this twist in action. Now, in this case, the twisting is up and down, right, around that left-hand side. It could be in and out. You know what I'm saying? So for us, we choose a pivot point. So what I did was I just selected this left side here. All right. Now I put it right on the place where that left cable anchors. I mean, I'm just talking about that being my twist, right? Up versus down. So if I were to cut this side over here, this right-hand side wire, then that thing would twist and fall that way, right? That's all we're looking at. Now, I pick the left side all the time because it's closest to the margin. You could pick the right side. It doesn't honestly matter to me. Okay? So here we go. All right. Choosing that location eliminates the torque from a 1,200 Newton force from our calculations. Again, if you think about torque as being force times distance, this cable is 0 meters from the pivot point. It would be like trying to open the door by turning the hinges or pushing right on that hinge spot. The amount of torque that's required to do that is exponential. You can't do it, right? So for us, that's where we start to pick. So we know that we have 0 torque there. Because it's at that point, that's why it works out really nice and really special for us. The lever arm distance at that is 0 by defining the point at this location. Now, the two recommendations I'm going to have, or the biggest recommendation I'm going to have, is put a pivot point like this either here or put it here. Put it on an edge. Don't put it in the middle. In the middle adds all kinds of craziness and weirdness and all kinds of different twist concepts. Put it on an edge so you can polarize everything either up or down. That's all you have to be aware of. Okay? the upward torque from the right cable should equal the downward torque, right? Because we're not getting any movement. So if this thing is truly stationary, then the upward torque, the upward twist, like this cable pulling this thing up and over the top, should equal Brian and the beam trying to pull this thing and twist this thing down. All right, so our torque down equals our torque up at this point. So what we start to see is what are our torques that we're acting here, right? Hey, dude, look at this guy. You gonna say hi? Huh? You gonna say hi? No, you shy to point? All right, get out of here then. All right, so our downward torque is Brian and the beam. Our upward torque is at 600 newtons. Now remember, why don't we include the 1200 Newton torque? Because that's at the pivot point. Its distance is going to be 0. All right, so the upward torque, well, its center, its place where it's pulling is 10 meters away. Think of this as our radial arm, right? So as we look at this thing getting all the way out there, that's 10 meters. All right. So because it's 10 meters, what we see as our upward torque is 6,000 Newton meters. Now, is there any other component of upward torque? You might say, well, yeah. Hey, there's this wire right here. Well, how far is it from the point? Where is its center of mass? In this case, that would be times 0, right? Because it's right on that. The distance is actually 0. So when we see this, our upward torque is 6,000 newtons. In order to, or Newton meters, sorry. In order to balance all of this out, our downward torque has to be 6,000 Newton meters. I mean, in order to cancel this completely, we have to see it being the same. So that works out really well for us. So if we have the 6,000 Newton meters downward, well, let's start with a beam first and foremost. Okay. So when we look at this beam, what we're going to see is we're going to take our force times our distance. Now, this is the part that is the most commonly missed. This is the big mistake piece right here. All right. And I'm looking around trying to see if I got my meter stick anywhere close, which I don't. But I'm going to say that my hole puncher is the beam, right? What I need to do is I need to figure out where is the center of this force. Because even if we think about, pulling the door open, if I pull a door open, the center of the force is right in the middle of my hand. If I push on the door, it's right in the middle of my hand. That rope that's fixed on there, right? That rope, the center of it is right at the bottom of it. So same thing applies here with our beam. Where is the center of it? Where is its focus, basically? So for us, the focus should be, do this, whoop, pretty much right in the middle, right? Now, again, this one's a little trickier just because it's got all kinds of paper and stuff like that, but hopefully you understand the point. Please be aware, whenever we talk about the beam, the center of that beam. So when we look at this radial, arm here for us, so to speak, right? That's the whole entire beam. So the beam for us really only matters to right about there. So if this whole thing is 10 meters, right, then the part that we care about is 5. So what ends up happening is we take its perpendicular force, because that's the force that's acting down upon them, right? In order to keep this beam from twisting, from torquing, from turning, from doing whatever you want to call it, we have to put that in the middle of it. Otherwise, you're going to get twist. All right. So 1,000 times 5 meters. What we find out is that just for the beam, it's 5,000 Newton meters downward. All right. Downward. So if the total torque downward is 6,000 Newton meters, and we have 5,000 Newton meters from just the beam, that means that Brian attributes 1,000 Newton meters of torque to it. Okay. So in order to find this, there's our torque, 1,000 Newton meters. We take the force of Brian times the distance of Brian. Well, we know the force of Brian is 800 newtons, right? That's his weight up here. Okay. So 1,000 divided by 800 newtons, that's going to be a distance of 1.25 meters from the left side. Now, please be aware, you have a quick check in place here, right? Notice that this thing is a 10-meter long board. If the distance would have equaled 11.25 meters, you messed up. There's something wrong about that, because that would put Brian somewhere out here, right? Which is not the case. He's not outside the beam. He's actually inside the beam, okay? So here's what I'm going to have you do. I'm going to have you hop out, make sure you get some practice time done with the practice examples for this question, right? I will make sure I have answer keys for that up for, the first hour of today, okay? But you have to run a bunch of these. And remember, the big area of mistake is the beam. Center of mass of the beam, where that force is perpendicular to it, is in the middle of the beam. All right? Sounds good. Talk to you.